In this video, we're going to talk about Faraday's law, which is the missing link that relates the electric and magnetic fields to each other that therefore later enabled Maxwell to tie everything together into Maxwell's equation as we know it. So when Faraday started looking for opportunities to create physical laws that he could name after himself, we already knew that current can create a magnetic field. And so in a way, since current is related to moving charge, which is electric field, that is a tie from electric fields creating magnetic fields. But at the same time, Faraday was thinking, well, then there's got to be a way for magnetic fields to create current of some kind, so that we have this interaction between the electric field and the magnetic field. So the key thing is we're trying to find a way to tie these two together. Up until now in electrostatics and magnetostatics, we were able to go from the electric field to the magnetic field in the form of current to magnetic field in Ampere's circuit law and the Biot-Savart law. Now, how about going the other way? Well, this is a little bit trickier to figure out because in this case, recall that we've been talking about electrostatics and magnetostatics. Magnetostatics, where the key thing is that the fields don't change over time. So you can imagine what I'm about to say next, right? So after a lot of work, Faraday eventually came across the discovery that is now known as Faraday's law, and it can be stated like this. So it involves the term electromotive force. So this is the electromotive force, which is in essence a voltage. And this is referring specifically to not just a voltage, but a voltage that is produced by a change in magnetic flux in the closed current path. So let's start by coming up with the expression for the closed current path. So if I take a line integral of the E field about a closed path, so the circle means it's a closed path. So if I take up all the DLs and add together, I form a closed shape and end where I began. This is going to be equal to, if it turns out that you're a toroid and there's a lot of loops, you might have an n here. If it's just a single loop, then the n is just equal to 1. But it's going to be equal to negative the change in magnetic flux over time. So remember, magnetic flux is the surface integral of the magnetic flux density. So we can also write this as minus d by dt of the surface integral of the magnetic flux density. This here is Faraday's law in integral form. So let's try to visualize this. Remember, this E dot dl is a closed integral, meaning that we have a closed loop of an electric current. So let's just say the current looks like this. So this is an electric field you integrate through. If it's a conductor, then it would just be the current going through a wire. And remember, it's a closed shape. Closed shape means that there's a surface that we can deal with. Now, if in that surface is a magnetic field, then there are going to be flux lines through it. And if the flux line changes, it's going to create a change in the current that's going through this loop. Or if in the case that there is no current, there's going to be an electromotive force or voltage that stems from this change. And if this line integral here is a conductor, then a current will subsequently form. Now this current is going to form in a very specific way. So let's say the current is increasing. So let's say the magnetic flux is increasing. So if something is happening, so the magnetic field increases, you have more flux lines going through there. So that means that d phi dt is going to be greater than 0. Well, what direction of a current does that happen? Remember, there's a negative sign here. So what that means is that as this increases, what's the corresponding current that you would expect to come out? So the corresponding current that you would expect would be, if you use the right-hand rule, it would be in this direction, right? However, the general concept is that the current that comes out is going to be one such that it will oppose the change in flux. So if we increase the flux lines, that gives you, if we're looking down from here, down from here, this would be, if I put my thumb here, wrap my fingers around, it would be in the counterclockwise direction. Now, the electromotive force that comes out will be such that it tries to counter the change in magnetic flux. So what that means is that the resulting current will be one that creates a magnetic field that tries to oppose what ends up oppose the magnetic field lines. So if the magnetic field lines are increasing, that opposes a change in magnetic field lines. So if the magnetic field lines are increasing, it's going to try to create a magnetic field that's opposite to it. So if you do the right-hand rule to that, you point your finger down, you're going to find that the resulting current and the EMF that comes out is going to result in a current that's going to go in the clockwise direction. So let me say it again in a faster way. So if the flux lines are increasing, that means that it will try to come up with a magnetic field that counters it. So you don't want to use the right-hand rule to the direction of the flux lines. You want to use your right-hand rule and point your thumbs in the opposite direction of the flux lines. And then when you curl your fingers around, that is the direction of the electromotive force. Similarly, if the amount of flux is decreasing, then that means that it will, in the case of if the flux lines are decreasing, so we have our closed surface here. If the flux lines are decreasing, then it's going to try to resist change. Remember, what it always tries to do is it resists change. So it will try to create, it will move in a direction such that a magnetic field will be created so that the flux lines going through will stay the same. Therefore, in this case, the magnetic field that it will try to induce will be in the same direction as existing magnetic fields, and so the current will instead, using the right-hand rule, will be in the counterclockwise direction. So this is the case where you have decreasing flux lines. There are several reasons that the flux lines going through might change. So reasons that you might have a change in the amount of flux going through. One is that the change is that the magnetic field changes. So there's a change in B or H in the magnetic flux density and magnetic field. So I just have suddenly more yellow arrows or fewer yellow arrows. But another way to do it is that if the shape of our integral changes, right? In the case of the loop, right? So if the loop dimensions or the orientation changes. So that would be another way to change the flux lines, right? If this suddenly was rotated out of alignment, then the effective flux going through would decrease. Or if it was rotated into better alignment, where the flux lines go, through it more normally, more at a 90-degree angle, that would also increase the effective flux. So changing the dimensions or the orientation, or changing the field itself, or both of them, will result in a change in flux. Now, one final thing that I'd like to point out is that you can also turn Faraday's law into point form. So this is the integral form. The point form, you can use Stokes' theorem, our old trick to deal with line integrals, to come up with Faraday's law in point form. So the EMF, restated, the EMF is going to be the closed loop integral of E dot dl, which is going to be negative the surface integral of B dot ds d by dt. Now remember that Stokes' theorem says that we can change the line integral into a surface integral of the curl of that vector field. So substituting that back in, we now have two surface integrals on either side. So if we shrink it down to a point, so we get rid of the surface integral, meaning we shrink it down to a point, then you are now left with that the curl of E is going to be equal to minus d by dt of the B field. So this is Faraday's law in differential form. So as a quick tie to the previous concept, remember before we had talked about how the closed loop integral of E dot dl is going to be equal to 0, right? Indeed, that was how we came up with the boundary condition that the tangential field across two materials is going to be continuous, right? Is because we use this fact. But remember, that is in the case of electrostatics land, which we are no longer in, because we are now talking about situations where the field changes. And so this is not necessarily incompatible with what we're learning now. It's just because we're talking about electrostatics, that means in magnetostatics, the field does not change with respect to time, so this is 0. But in reality, if we are not bound by purely electrostatic and magnetostatic situations, then situations like Faraday's law will come into effect. So in summary, we came up with over here the missing link where a field can create a current, which opens the door for electric fields and magnetic fields to self-reinforce, and where one can create the other and vice versa. And the missing link here is Faraday's law. Simply stated, it states that an electromagnetic motive force, which is a voltage, but a voltage specifically created due to the change in flux lines. This electromagnetic force is going to be oriented such that it counters any change in flux. So if we have an increase in change in flux, then the electromotive force and the current that's created will be such that it works in the opposite direction of the external magnetic field. Similarly, if the external magnetic field and flux going through is decreasing, then the electromotive force will be such that the magnetic field creates is in that direction to increase the flux lines. So the take-home idea is that basically if you have a loop of a conductor, it doesn't like changes in magnetic flux going through it. And if the amount of flux going through it changes, it's going to do everything it can to fight it. I think that's the key take-home point. And here we have it in the integral form. Again, closed loop integral E dot dl is going to be equal to the change in the magnetic flux going through it. But we can also use Stokes' theorem to reduce it into point form, which is the curl of E is going to be equal to the change in B field. And so again, remember in electrostatics land, we had said that curl of E is equal to 0. That is no longer the case if we open up the possibility of changing magnetic fields. And so now everything is set up for Maxwell to come in, throw a bunch of concepts together, and have a set of equations that we can remember him by.